the set of differential equations that model your system. But this is not hard because if you have a rational network model, you can use computational tools to apply the law of next action and automatically build your set of differential equations from your rational network model. Then what is really difficult here is to build your rational network model. But if you are a biologist, you are in much better condition to build your rational network model. If you are a biologist, you are in much better condition than if you are a biologist, because the biologicians, they are very good here. They are very good to solve or to calibrate the system of differential equation. But they are not good here. They are not good to build a rational network model, because to do that, you must know about biology. So the message here is, if you are a biologist, you are in a very good condition. Then I will talk here about how to solve the difficulties here. Because here, there is no recipe. I have no recipe to build a rational network model. I do not have a universal recipe. I have some recipe that is the recipe I have been used, but it does not mean that this recipe is useful for you. If you are a biologist, if you know about your real world system, you are able to decide what is the best recipe to build your rational network model. So here we are talking about this step that are the steps that can be these steps can be built in a computer. Okay? So the idea here is the following. This is a simplification. We have a biochemical process here, a very simple biochemical process at the dimerization. Then, from this biochemical process, you build your rational network model. Here, your biological background is very important. Okay? So, if you have your rational network model, then you can use the law of next action and build your original differential equation model. Here is very simple. Okay. So, if you have your original differential equation model, the first question is, how does my model behaves in its stationary state? Then you find the algebraic equation that describes the stationary state of your model. Then, of course, if the model has any conservation equation, then you calibrate your model and you solve your model, and you reproduce the experimental data you get. Okay? This is the way that the preference uses to solve differential equation. But they say to me, okay, Francisco, but this is a very simple system. What happens if we have a more complicated system? Here, there is one story about this model. When I showed this model to a mathematician in a meeting, they said to me, Francisco, this is a very complicated model. You can reproduce anything you want with so big number of kinetic constants. So, in the same year, I went to a meeting to another meeting where I showed the same model to a biologist. And they said to me, Francisco, you wanted to reproduce a biological system with so simple model? That's not possible.
O artigo que nós mandamos.
That's what we can do with so simple, not so simple theoretical model. So here we have the reaction that network model. Then we use the mass action law, and we find the set of differential equations. Now, this is more realistic model, meaning that the differential equations are very hard to solve. Then it's very hard to reach this. It's very hard to calibrate model with so huge. How to solve this? Use a table graph network. If you use the chemical reaction network theory, you will simplify the solution of your differential equation. So this is the strategy we use to facilitate the charge of solve your set of differential equations. The first step to apply the chemical reaction network theory is to make a vector representation of your reaction network model. I don't have time in this meeting to explain to you how to make a vector representation of your reaction network. If you want to know about that, you must go to the nano-biosystem. I was graduate.
Mas eu acho que vai.
Where you have.
Estou escutando alguém falar, tá entendendo?
University of the Rio de Janeiro, o FRJ, Biomanguinhos, IMEC, o Campo de Caxias, and the LNCC. Okay. So this is the discipline we talk about this, about the issue I'm talking here. So, but in this very short mid course, I will talk about overview is strategy, the concept of by stability. And today I will talk. I finished the overview of this strategy, and now I will talk about the concepts of biostability. Tomorrow I will talk about the law of mass action with a little bit about the vector representation of the interaction network system, and I will finish my talk tomorrow, talk about modeling dorsal and can be self-significant as an example how to use differential equation model to analyze your data.
Será que essa blusa vai ficar curta com aquela calça que eu tô usando?
So let's talk then about the concept of
Tá encolhido.
stability. I talk here more to biologists. Okay. The idea is why should we try to understand the concept of biostability? Because we want to use the concept of biostability in developmental biology. Then I will make intermediate step. Before we talk about biostability in the developmental biology, I will talk about biostability in our microscope real world. So this is what I'm going to talk today. Let's make an imaginary experiment. Let's see, we have a rod, a magnet, and a magnetic table. Okay? What are the variables here, and which are the parameters? So the variables are the rod height and the rod height and the distance between the magnet and the table. In which who is the parameter is the rod's constant key. Okay? So here are the variables, and here is the model parameter. So, it is an experiment. I will move the rod, so I will change the rod height, and I will measure the distance between the magnet and the table. Okay, let's do the experiment. So I will move the rod. I will move down the rod and moving. Have you imagined what I'm going to happen? I'm moving here. So in some moments the magnet jumps and go to the table. So now I still move the rod, but nothing happened anymore. Now I will make the opposite direction. I will move the rod up. Move the rod up. Then it will delay the magnet here is still together the table, but I will move more than the magnet now jump. Now the magnet is there. Then I still move the rod and rod height. This distance between the magnet and the table. Both are 50. Now I move the rod and I have the new data. The new rod height here and the new distance between the magnet and the table that is here. Now I will move again. Then okay. Again, then now we can see that the magnet jump. Now the rod height is about 5. The rod height is about 5, but the distance from the magnet to the table is already 0. Okay. Now I'm moving again. Here is changed because I reduce the rod height, but the distance between the magnet and the table is not changed because it's already 0. Okay? So I finish. Now let's take the data about the opposite direction movement. So here I'm moving the rod up, and you can see here, now we can see the difference because here the height is around 7, but the distance between the magnet and the table is still 0. Okay, that's the data. Then now the magnet jump oscillates, then reach the stationary state. Okay? Then let's move again. Okay, so we have the real world behavior and we have the data. Now let's understand the behavior. So you can see that you have 2 trajectories. The up to down trajectory and the down to up trajectory. And we can see that the trajectories are very different. So one time more, okay? Let's repeat half of the experiment. Let's move the rods until I reach the rod height around 8. So here the rod height is 8. Here I register here the rod height is 8. What is the distance between the magnet and the table? Is 8 too. Okay, perfect. Now let's stop here and let's now make the order way. Here I make the experiment here and I take the results here. Okay, let's see. Let's stop here. Now this is very important point. I have one question to you. If H is 8, how much is D? It means H, the rod H is 8. What is the distance between the magnet and the table? Who knows the issue? The issue is a little bit simple. If we start up to down, we know that D is 8. If we start down to up, G is 0. What does it mean? That this system has two stable stationary states. It means that this is a bistable system. A bistable system we can define as the properties of the system that have two stable stationary states that we can also call fixed points. Now, let's suppose that I make this experiment here and you do not see where I start from. I make this experiment here, high, and you do not see the moment where I start. But then I move the experiment here and show to you that the magnet is together the table. If the magnet is joined to the table, you will say to me, Francisco, you start the trajectory down to up. You know that I start the trajectory down to up, but you didn't see I start the experiment. But you know, you see the experiment now, you know about the past. What does it mean? What is the property that makes us know about the past? Memory. This system has memory. If you see where the system is, you know where it starts. We know where the system was in the past. So, this is memory. But in physics, we call memory as hysteresis. That is the property of the system choose energy state depends on its algorithm one. It means that a system that has memory. So we can now simplify, and if you have a model, you will know that we have some unstable stationary state here. That is here in the reality is the position where you can equilibrate the magnet in the middle way. Oh, but this is very unstable. Any fluctuation will move the system to one side or to the other side. So this is unstable stationary state. So if you have the model, you will be able to determine the set of unstable stationary states. So this region where the system has two stationary states accessible, they are called the bistable region. So I finish now talking about by the definition of by stability, and tomorrow I will talk about the law of expansion, the vector representation of a reaction network, and I will talk about one example. Thank you very much. Questions?
Question? Any question? In the chat?
I saw some questions there. So, Okay.
No question. For the moment, no question.
Thank you. Thank you.
So let's take again. So at 10:30 we have the next speaker. 10:30, no? Yes. So we have a small pause up to 10:30. So 10:30 we have the next speaker, and so see you in a short while. 10:30. Okay.
Às 10h30 é a área.
Sim. Estou colocando a sua fotocapa de maneira que ela fechar isso aqui.
Esse é o laptop do Francisco. Vamos, deixa eu desarmar aqui as coisas aqui. Vamos lá. Já vou sair mexendo aqui. Stop share screen. Deixa eu minimizar aqui. Francisco, tomei a liberdade de mexer aqui, hein?
Tudo bem? Tudo bem, graças a Deus.
Tomei a liberdade de mexer agora.
Oi?
Tomei a liberdade de
Ficar
mexer
à vontade.
aqui. Pode fechar, cara?
Fechar.
Pode fechar?
Tá,
PowerPoint?
pode fechar.
Então tá bom, vou sair fechando aqui.
Que tem o seu PowerPoint, né?
Cadê as coisinhas aqui? Ih, Live Meeting? Não quero Live Meeting. Não. Tá bom, podemos espetar.
É a última coisa que eu trouxe, é uma apresentação.
Ah, é?
Abdelhai.
A professora Eliana, ela... Né?
Abdelhai.
É a pessoa que eu conheço que tem um pedacinho de cada...
É, um pedacinho de cada nacionalidade.
Abdelhai, Furquim, Werneck...
Saul, Furquim, Werneck,
é.
Abdelhai.
De onde é originário?
Abdelhai é libanês, é do meu marido. Ele é neto de libanês.
E Saul?
Saul é judeu.
Saul é judeu.
É judeu. É judeu, sefaradi.
Furquim nasceu lá.
Não, todo mundo nasceu aqui. Furquim é francês, é Furquin. Werneck é alemão. Você vê que é só não tem chinês e russo.
A pessoa que
Mas o resto tem tudo.
A professora é... Bem, está instalando aqui. O software não pode ser instalado com êxito do que com o software de driver. Não entendi por que não poderia. Bem, foi, acho que foi.
Aí bota a última coisa.
É um arquivo ou uma pasta?
Não, é um arquivo. É um PowerPoint.
Apresentação 1.
Isso.
19 essa aqui, né?
Essa.
19 do 7.
Foi feita ontem.
19 do 7, então tá bom. Vamos lá, apresentação 1. Conrado, enter the waiting room. Ah, tá.
Sim. Deixa aí, tá?
Ok. Então já estamos... No princípio, estamos prontos aqui. Admit, tá. Eu tô como host, né? Então, deixa eu botar aqui. Se a gente tá... Oh, maravilha. Aqui, professor, a gente tem até o pointerzinho que funciona aí. Se quiser, é só pular aqui. E aqui é o laserzinho, se você quiser
Certo,
apontar.
para apontar, né?
Quiser apontar.
Uhum, tá.
Beleza. Então,
Agora, mas ainda tem uma
We are
abertura, né? Não tem abertura?
vai ter abertura? Vai agora a abertura? Quando é que a
Teoricamente,
Denise não ia falar
abertura
agora?
é agora, né?
Elas estão em Portugal.
Ah, mas não ia falar, não vai falar online, não?
Eu sei.
A Cristina queria falar, mas ela está presa numa reunião.
Calma aí, calma aí.
Planejou uma abertura, mas não teve. Como seria uma abertura?
Não, porque normalmente era a nossa leitora, que foi fora, e normalmente teria a leitura do fórum, que está presa na
Calma aí,
reunião
gente, eu tô
com
perdido
os
aqui.
construtores. Aí ela falou, ela queria muito, porque ela é da área de biologia. Porque a gente tem uma nova, Cristina Erutel, que é do...
Eu não sei, Stefania, não sei como é que faz aqui para
Sim, bioquímica.
fechar aqui, não. O
Tá
Zoom
bom,
não
tá
aparece.
bom.
É melhor fala.
O que é? Então, mas vamos esperar ainda 6 minutos. Mas tem que baixar o Zoom, porque senão não dá para amanhã. Hoje ele baixou o Zoom, senão
Né?
é muito... Vamos esperar.
Você sabe se tem um toalete?
Sim, se vai lá você vai um papel higiênico para a toalete e tudo?
Não, eu trouxe. Botaram lá? Não das
Se
mulheres,
você
dos homens?
trouxe uma,
Das mulheres aqui.
Papel higiênico?
Botei os dois.
A Stefania está falando que acha melhor você instalar o Zoom aí.
Instala.
Instalar?
Aproveita esse intervalo.
É, então, estou falando. Mas como é seu, eu não quero ficar mexendo.
O computador é da universidade.
Como é seu, eu não quero ficar mexendo aí.
aí sim,
Não, o áudio daqui.
Esse, não, ninguém vai ouvir nada.
Tá certo.
Você vai, o microfone está conectado ao computador?
Não,
Ah, então tem que ter o áudio. Aqui tem o áudio.
tá bom. Tem o áudio. Tá certo.
Deixa eu ver. Como eu dou aqui? Tem o áudio do Logitech. É melhor.
A minha é essa também, muito boa essa câmera.
Bom, então, podemos começar. Qual é esse? Esse, não? Então, melhor tirar eu vou transjuntar. Melhor tirar a máscara. Então, bom, espera que eu tire aqui. Durante a experiência. Então, um prazer ter a Eliana Abdelai, que nos vai falar de Identifying Targeting Cancer, the Need for System Biology. Então, Eliana é da Universidade da PUC, de Física.
Depois eu fui para a Biofísica da UFRJ.
Ah, ótimo. Da Biofísica da UFRJ. Acho... Assim, sorry. So she's formed in physics from the PBL, and now she's in biophysics of the Federal University of Rio de Janeiro. Sorry, we have some Brazilian English.
30 years at the Federal Rio de Janeiro, and then I moved to Inca, of cancer. And so for 20 years, the last 30 years, I have been working in Inca.
So please, Eliana, you're very welcome to start actually the first seminar of our conference. So we're very pleased to have you. Thank you.
I want to thank the invitation to participate in this symposium. I don't work really in system biology. I work in the basis of system biology and try to identify biomarkers of diagnosis, prognosis, prognosis and treatment and monitoring in cancer. And I will show you how we do this and why we need system biology.
É porque o Francisco pegou para instalar aqui o Zoom.
So the title of our talk today will be Identifying Targets in Cancer, the Need for System Biology. And why study cancer? Cancer is a public health problem nowadays. It's the second cause of death in all the world, and here in Brazil also. And 20 million persons live with cancer nowadays in the world. The treatment is of high complexity, very expensive, and the government the public policy needs to support this treatment. So it is really a problem. And we need to identify methods and manners of treating cancer preventively and beginning of the disease so that it doesn't cost so much. Okay.
Só um minuto.
Eles não estão vendo.
Because the people online is not seeing the
Okay.
share screen. So they were seeing you, but not seeing
the slides.
the slides.
É isso que eu não estou conseguindo fazer. Share screen.
Nowadays, the first cause of death in Israel is the cardiovascular disease.
Não.
But each time, the development of medicine in this field is so great that people don't time anymore of cardiovascular diseases, and cancer will be in less than 10 years the first cause of that. So it's really very important to attack this problem. Okay.
No, it's working now.
I hope that is
Okay.
And what's cancer? Cancer is not one disease, it's several diseases that can attack several types of cells and several types of organs. The most common cancer attacks epithelial cells, are the carcinomas. Less commonly, we have the hematological melanomas, leukemias, and lymphomas, and less common soft tissue attack, becoming sarcomas. But the most common, 90% of cancers are carcinomas. And what is a carcinoma? It's a disease of the epithelial cell. Carcinoma in Greek says epithelial. So this cartoon shows exactly how cancer starts. It starts with one cell being attacked by external substances or physical attack, so that one cell loses its capacity of differentiation, but gain the quality of being efficacious. One cell. The epithelium is made by differentiated cells. In a differentiated cell, it doesn't replicate anymore. It doesn't duplicate the cell anymore. So those cells have a lifetime, and then they die, and new epithelial cells will cover the supervisor. But this cell here gain exactly the capacity of continuously replicate. Okay, so if you persist with the mutation, it has gained for a long time. So, of course, one cell that is attacked, we cannot see, we cannot sense. There is no symptoms about it. Okay, so cancer starts much earlier than the appearance of cancer in a person. Okay, so this is the natural history of cancer made by a famous epidemiologist. Normally, we are exposed to risk factors, and of course, the epithelial cells are those that are in more risk because they cover our outside and also our inside. Okay? So these cells are submitted to several risks like sun, like X-ray, ionizing energy, agrotoxics, for example, that we in our ingest and etc. So these risks, these factors are capable of changing one cell. And this cell is here, but the disease only begins here because these cells have replicated several times, and now you don't have one cell, you have several cells. And you start to see the disease. First as a dysplasia, then as a carcinoma. Normally, when we do screening in the population as mammography, cytopathology, biopsies, etc., we can detect early the disease. But there is a time to the appearance of the symptoms. And here it starts when we really say we are with cancer, and then the treatment for symptomatic patients. So if we can identify the disease here, it will be better because the treatment will be easier and more effective. But in general, we see the patient here when they are very advanced disease. And so it's very problematic the treatment of this patient. Sometimes you can even make the surgery because the tumor is so big that you can't take it out. You have to treat the patient with chemotherapy so that the tumor diminishes, and then you make the surgery and then you make chemotherapy again. So this is the problem. As we are here, we don't have a very good response to treatment, and also we can relapse after the surgery.
Não dá sim.
Não pode.
Eu tô ao contrário.
No problem. The problems that are going on. Not going on.
Sorry.
Okay. So here we can see the stages of progression of carcinoma. Normally, what we have in the epithelial tissue is that a basal layer is in yellow, then the cells, the epithelial cells that are still capable of replicating, and those cells that of the connective tissue that are completely differentiated. When you suffer an attack to these cells, you will get much more cells that are still capable of replicating. And this is what we call dysplasia. And this dysplasia can gain new mutations so that it starts as a carcinoma in situ. And if this carcinoma gets the capability of invasion, it will invade the tissue, they will enter the circulation, and they will do metastasis. And then we call it the malignant carcinoma or malignant carcinoma. what this means in molecular mechanisms. A normal cell here has a normal DNA without mutations. One of these cells suffers a mutation, normally in an oncogenic gene, and we call this a driver mutation. It will start the process. It can be an oncogenic driver, a gene being mutated, or we can have epigenetic alterations, and I will explain epigenetics. These cells will proliferate more, and we will have carcinoma in situ, where normally it occurs new mutations in tumor suppressor genes. An oncogenic gene, it functions as a dominant mutation. What's this? We have two genes. On each gene we have in our body. Each cell has two copies of each gene. For an oncogenic gene to be mutated, it suffers only one mutation. Only one gene will be mutated, and we will have the result as an activation of a process like replication. But suppressor gene is a recessive gene, so you need to mutate the two copies for that cell. Okay, so this gene will lose its activity and will lead the progression of the tumor. Okay. So during this process, this progression, the cells acquire several new capacities. Not only the first one that was the capacity to replicate indefinitely, but also several other processes are changed so that they are called cancer hallmarks. So this is the first one, the sustained proliferative signal, that is, the cell is always proliferating, and the cell can make growth suppressors. So she does not respond anymore to growth suppressors. She avoids the immune system response that you have to free ourselves of any attack. If you have anything attacked by a virus or a bacteria or a mutation, the immune system will say this cell is not good anymore, it has to be destroyed. But during the process of cancer, we have this immune activation that makes this immune system from antitumoral to protumoral, okay? And several other processes that are activated. Well, besides the mutation in the genes that will change the function of the cell, we also have what we call epigenetic mutations. And what is epigenetic? Is changes in the DNA that are not changes in the nucleotides. A, B, C, G are the nucleotides of the DNA. So the mutation normally deletes one of these letters or one of these molecules, or change it for another, or amplify it. But in epigenetics, we don't change the nucleotides. It continues to be the same sequence, but we can manipulate DNA and the C's followed by G's. There is in the genome we have CPGs, islands, CG, 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 CG. So these islands are methylated. So the cytosine receives one methyl residue. So this methylation is a sign. It's a sign that this gene is not going to function anymore. Okay, so this gene will be recognized by enzymes that will close this region, and so this region will not be transcripted anymore. We will not have RNA from this region. Okay, so methylation is something that changes the expression of the cells without changing the DNA. Okay. Another possibility is histone alterations. Our DNA are involved in histones, proteins. Histone proteins are basic proteins that are very close to DNA, that are acids, so they make connections, and the DNA is organized by the histones. And changes in the histones, methylation, acetylations, and phosphorylations, change the affinity of these histones to the DNA. So you change the capacity of closing DNA or opening DNA. It depends on the histone alterations. Okay? So these are several types of mechanisms that changes the expression of one sector of DNA without changing the sequence. Another thing that is very common are regulators RNAs, microRNAs, or non-coding RNAs. Are RNAs that do not translate in proteins. They only regulate the expression or the translation of the RNA in messenger RNAs of the cell. Okay, so the expression of different microRNAs or long RNAs will change the expression of the cell. So I'm going to give you one example. For example, a B cell. A B cell, it passes for several stages during the differentiation of the cell. A B cell can, if mutated, derive an acute lymphoblastic leukemia of B cell. Okay, so what types of alterations we find in these leukemias? We find, for example, mutation in a
Então você pensa no
DNMT2. This enzyme is the responsible to methylate DNA in a cell. So if you have a mutation that changes the function of the enzyme, she will methylate too much, or she will not methylate. So the cell will not have the perfect code to her expression. Another mutation that we will find is, for example, microRNAs that are differentially expressed. And there are several microRNAs expressed. Or this one is the tumor suppressor gene. Can be upregulated and so derive that cell with this mutation will start acute lymphoblastic leukemia. These cells are precursors of these cells, very early differentiated stages. But you can have a naive cell that is a differentiated cell, but that do not still have been activated to produce antibodies, for example. And this cell, the function of it is to produce antibodies. So in naive B cells, there are another sets of mutations that are found. Depending on the mutation, you will have chronic lymphocytic leukemia. For example, mutation in RU1 RE1 is an oncogene or microRNAs, the regulator, for example. If this cell, and she leaves the bone marrow and goes to the lymph nodes, and at the germinal center, where this cell is going to be checked to start to present antibodies, another set of mutations can occur and will give lymphomas. The Burkitt lymphoma, follicular lymphoma, etc. Large cells lymphomas. And if this cell has been already released from the lymph node, is in the circulation as a plasma cell, there are other mutations that can occur and produce a multiple myeloma. So the mutations, the alterations of expression, at each point of differentiation of a cell will produce a different disease. Okay? So cancer is not the result only from mutations on oncogenes and tumor suppressing genes. That was what we saw and that the first cartoon. But also the result of changes occurring in the expression pattern of the cell. So what really the cell is doing is producing in terms of RNA and proteins, and how these molecules are functioning is that any alteration will cause cancer. But cancer is still more complex than this. It's not only a disease of the genes. Okay, it's a disease of the genes, but also of the environment, because are the risk factors that mutate the genes. Okay, so if you look at genes mutated in several types of cancer, you'll see that there is very few genes being mutated as the cause of the disease. But the environment is really important. So you see infections, tobacco, diet, alcohol, obesity, and several others. Okay. More than that, the cells, we are in an environment, but the cells are in a microenvironment. So the cell that mutate in a ambience, it is near several other cells that are talking with her, that are secreting substances that has an activity in the other cell, that can be alphacrine, paracrine, endocrine, etc. So we have several cells in the microenvironment that are important for the preventing tumor growth or to helping tumor to grow. So, in fact, our immune system should stop any cancer, but it doesn't, because the cancer cells are very intelligent. They make a way of the cells of the microenvironment not to have an attack function against them, but in other ways, adds to continuous proliferation, okay, and getting new mutations. So, as far as we understand each of these steps, we can design drugs directly against this activity. So, in this cartoon, for example, we have several
Ele está na bateria.
Aqui. Dá para botar nesse slide que está aqui? Esse de cima. Sai e entra novamente. Vai para o cheiro.
Sai. Chama. Adriano? I need you. You are the expert here. She asked me to stop sharing and share again. Stop sharing, share again. But o que está acontecendo aqui? Acho que você está com os dois aqui, será? Esse aqui faz todo. Não, tá vendo? Ah, não, tá pra lá. Calma aí, calma. Ah. Oi? Ah, tá. Ah, calma aí. Calma. Aí tem que transportar para cá aqui, ó. Agora vai. Perfeito. Foi?
Coisa que aparece aqui não aparece lá.
Ah, é? Foi agora?
Agora
deu?
aparece.
Deu? Foi? Tá, deixa eu só clicar aqui para ver se vai funcionar.
Yeah. So, as you can see, there are a lot of new drugs being tested or in the market for exactly each of the communications, the targets that have been identified in those processes. Okay. So, the big challenge is how to identify targets because the system is so complex that it's difficult to see exactly what is happening, have a portrait or what is happening in the cell. So to do this, we need much information as we can. Okay, so if we can examine the genome, the exome is the genome that's being transcribed. Okay. If we can analyze all the expression pattern of that cell in that condition, the methylation. There are several students there. The metabolomics, the proteomics, the microRNAs, and also the microenvironment. We can analyze all these and integrate all these.
Não foi? Não. Continua com o resume sharing, né? Agora foi?
Não.
Não, vem cá, mesmo assim.
Não.
Desculpa.
Okay. So we need to have all this information, the much quantity of information we can, and integrate this information and to understand how the cell is making her life, and to identify the targets that could be of help for diagnosis, prognosis, treatment, etc. So for this, we need large-scale platforms. What's that? We can have a complete view of what genes are being transcribed, what genes are being translated, what microRNAs are being activated or deactivated, etc. So we need this large-scale platforms. And what is this? Não vai. Alguma coisa tem que deixar de fora.
Tem que clicar aqui, foi.
So we enter the omics genes, the omics time. What is omics? Is genomics, is the analysis, the complete analysis of DNA, the complete sequencing of the exome or the whole DNA. The transcriptomics, the complete analysis of gene expression. Neuronomics, the complete analysis of microRNAs that are being transcribed and produced. Proteomics for proteome, and metabolomics for metabolome. And if we have as much as we can of these informations, we can understand what are the alterations in these cells that are tumor, what are the networks or the pathways that are being alterated, why the cell is not doing this but doing that. Okay, so these networks and pathways is what we want to understand what is happening in the cell, and then try to project this for the cell or the tissue phenotype. What are the tools we have to identify these omics biomarkers? We have genetic markers that we can identify by exon X sequencing, by whole genome sequencing. We can try to do some very few biomarkers by PCR or by in situ hybridization, fluorescent in situ hybridization. So we can identify single nucleotide polymorphisms or change of one nucleotide. We can copy number variation, the number of amplification of a gene or part of a gene. Also, we can do this by PCR. So we will have a genetic biomarker. But we can also have an expression profile by RNA-seq or by microarrays. We can identify the freshly expressed genes, so we can have expression biomarkers. We can do proteomics and have a proteomic biomarker, or a metabolomic biomarker, or microRNA biomarker. For microRNA, we can make it by RNA-seq, microRNA-seq, or microarrays also. Proteomics are normally mass spec. After we identify a biomarker, we have to validate it. And the validation is the more difficult part of the thing. If you identify a candidate, you can identify, for example, 1,000 molecules, but after you check it in a great number of samples from all ethnicity, you will have at the end 1% of them that can be a biomarker. So that's the process we do from the bench or from the sample, the patient sample, to the bedside, to the treatment of the patient. You will have to pass by all these passes. The biomarker discovery by proteomics, genomic metabolomics, image technologies, etc. You can confirm it normally by integrating this information, all this data. Then you have to validate it in a large number of patients and then check the validity of it. Then you can make a clinical test. So it's a long way from a biomarker to a clinical test. And to help us with the data, because we generate big data, so great number of molecules that we identify that we need help with data analysis. And for this, there are several softwares already in the market that we can use and use it. But sometimes we need to go further with bioinformatics. We need to create new softwares to help us. So this is the complete process. You identify the question you want to do, you design your study, what you want to do, what samples, then you prepare samples, you do all the analysis, genomics, proteomics, metabolomics, etc. Then you make data analysis, you produce the integration of this analysis, and then you identify some biomarkers. From millions of molecules, you identify some biomarkers that you have to validate. From these, one or two will be validated and then go to the clinic. So this cartoon shows the first part that I told you, molecules and pathways. But then you have to integrate this with the other cells in the organ to understand the system as a whole. Okay? So you have to include data from cells, from tissues, and from the whole body, because we have communication between cells that are very separated in our body. Depends on the type of the tumor, you have to consider the information that comes by endocrine information, for example, not only from endocrine parameters. Okay? So this is system biology. So you see, it's very, very complicated. At the beginning, we thought of cancer with this paradigm, perturbation in one cell that could reflect in some process in one cell type. But now we think like this. You have a perturbation, but this perturbation in one cell can create a perturbation in all the tissues. Okay, in several types of cells, maybe the complex of the disease. It's because of that that sometimes a drug don't do the function that is waiting to do, or do 20%, 30%, and not 100%, because you attack the cell that you study, but you don't attack. Okay, so So now I'm going to give you two examples. The first example in breast cancer, it's a paper published by us, where we were identifying biomarkers in the plasma. Biomarkers that could be helpful for screening. Okay? Because to screen a population is not an easy task. This is the progression of breast cancer. The normal epithelium, you have the basal layer, the epithelial layer, and the cells around. When we have hyperplasia, some of these cells are more proliferative than the normal one, but these cells, at the time they proliferate, they gain new mutations. So we can have atypias, what we call. The morphological aspect of the cell are not normal anymore. Then this could grow to make ductal carcinoma in situ, and then these cells acquire the capacity of evasion, and we will invade the tissue and make metastasis. And this is a carcinoma invasive. So, the carcinoma in situ, and principally the carcinoma invasive, has been identified as several subtypes. So, breast carcinoma has seven. It can be in situ or invasive. The invasive ones can be several types of tumors, and they behave different, they respond different to the medicine, to the drugs. So we have the luminal A subtype that is only cells of the luminal epithelium, those that starts to proliferate, that are more proliferative. They are most of them are luminal A, and they express the hormone receptors, estrogen receptor and progesterone receptor. They are normally very low grade, or they are well differentiated tumors, so they proliferate very good. And they can be treated by endocrine therapy. Okay? They are treated with trastuzumab. Sorry, with vaccines. Then we start to have the expression of HER2. HER2 is the epidermal growth factor. So epithelial cells grow under epithelial growth factor signal. So this is the epithelial growth factor receptor. It's amplified in those tumors that will be HER2, only HER2. They will not have any more the expression of growth receptors. They will have only HER2. And we have a luminal B in the middle that has low HER2 and low estrogen receptor. Those cells are more grade 2 than 1. They are large tumors. They have poor prognosis. And nowadays, as we know that they have the amplification of HER2, there was an antibody developed, the trastuzumab, that blocks the signal by the connect with the receptor and block it. So it's a good drug. And we have the triple negative that don't have PR, nor PR, nor HER2, that are normally high-grade tumors with very poor prognosis that don't have any medicine to treat it, because we don't have targets. We need targets to develop drugs. So what we did in our lab was to try to identify markers in the plasma of the different subtypes of breast cancer. So we took patients luminal hair, HER2 and triple negative, and also healthy controls, plasma. We did proteomics of this material and analysis with the Metacore. That's one of the software we use. And then validate these markers by Western blot in a bigger cohort, but not the bigger cohort I wanted to. So these are the proteomic results. Proteins that were down-regulated, proteins that were alpha-regulated, and this is a Venn diagram showing proteins that were common to all subtypes and proteins that were specific for each subtype, down-regulated or up-regulated. And so we analyzed this in more samples by Western blots, and what we found, for example, here, Iroquois-1, for example, is expressed in more aggressive subtypes and nothing in healthy donors. BCAS is the breast cancer antibody, nothing in healthy donors, and principally luminal hair and HER2 patients. And for example, Iroquois-5 expressed in all subtypes and nothing in healthy donors. So that these would be the best biomarkers we could identify with one study, only proteomics. Okay. So the idea is this was found in patients with cancer. Okay, that we knew exactly what subtype of cancer they had. But can we use these markers for screening of the population with the population that don't know that has cancer? Would we identify these markers if the patient has hyperplasia only? And this would be very at the beginning and would be a very good biomarker for screening. But for this, I have to screen 10,000 samples from hyperplasia to cancer. And we are doing this by targeted proteomics. So first example I wanted to show. The other example I want to show is on gastric cancer. Is on gastric cancer. Gastric cancer is one of the most common cancer in Brazil, and it normally appears very advanced. So people have a very low survival. In 5 years survival, we will have 20% of patients alive. The rest will have to die. Gastric cancer is in 80% of cases has the infection of H. pylori, and then 10% of tumors has the infection of adenovirus, Epstein-Barr virus. And we don't know that we have at least 2 types of cancer, of gastric cancer, the intestinal gastric cancer and the diffuse gastric cancer. The diffuse gastric cancer is a consequence of a mutation in ECAG, the protein ECAG, and is normally familial, it's hereditary. And the intestinal gastric cancer is the more common, it is exactly this one infected by Helicobacter pylori. In this study, what we did was to take the TCGA data bank, the patients from TCGA, all the patients with intestinal gastric cancer patients, The tumor tissue expression and also the non-tumor adjacent normal, no, that's called normal. And we looked for the differential expressed genes and the differential expressed microRNAs. Those genes, differential expression, and the microRNAs were interconnected. We analyzed the interplay between them, and then we integrated more also the differential expressed proteins that we did with gastric cancer patients. All this network was visualized in a very complex interconnection, and we identified 20 hubs, the genes that interconnect all the conversations between proteins, genes, and microRNAs. Those 20 genes were then analyzed for functional arrangement, code investigation, proctor, survival analysis, and validation for. So here we have the RNAs, the clustering of RNA samples with tumor and non-tumor. The blue ones are the non-tumor. You can see that there is a very clear difference between tumor and non-tumor. Those genes can differentiate very clearly what cells are tumor and what cells are non-tumors. We did a separation of 1.5 times more expressive. So these are the genes that we consider normally, and these are the differentially expressive genes. Those differentially expressive genes were separated from the rest by the interaction of the microRNAs that are shown here. Here are microRNAs, clustering of microRNAs, and non-tumor microRNAs. And also we identified those that were more commonly connected with the others, interacted with the others, and between those RNAs have been separated. Here is to show that we have the interaction between differential expressive genes and differential expressive microRNAs. What we call something important. A microRNA, what it does, or the upregulation of a microRNA make its target be silenced, not expressed. The RNA that is targeted by this microRNA will not be expressed. So the microRNA is a regulator of transcription of the target genes. But more than that, a microRNA also can change the translation of a gene. So for the interaction of a microRNA with a gene, for example, we have, for example, a downregulation of the microRNA is making an upregulation of the gene. So we have to have blue in one, in red in the other. If we have red and red, it's not functional. It's not happening nothing because the microRNA is upregulated. It has to downregulate its target. So we can only consider a target if we have a contrary regulation. Okay, up, from a down. For example, here we have a microRNA upregulated and a gene upregulated. But we know that this is not true. This has been identified by in silico, but in vivo it will not function. It will not be real. Okay? So if only can be real this. So we have the tools to analyze, but we have to look them and to understand what's happening, because not ever the thing is real. Okay? And if we think that this can be real, we have to prove it. Okay? We have, for example, to upregulate this and see if this is upregulated in the cell. We have to transfect the cell with the microRNA and see the expression of the gene. Or we have to do the knockdown of the microRNA to see if the gene is upregulated. So everything that we see in silico, we have to prove it. What we saw from all this, well, here we have the interaction of the 20 more active interactions. Okay, so if we have, you put all the interactions between DAGs, DAMs, and DAPs, you have much more than this. This is only the 20 that has more connections, okay? And as you see, it's a lot. The ellipses are the differential expressed genes. Those that we call diamond form are the microRNAs differentially expressed. And the squares are the differentially expressed proteins. Okay? And so I put here only those that are the 20 hubs more connected. I took out all the other connections with other proteins and put all the connections between them, the 20 more connected hubs. Okay, so these are the 20 more, and as you see, you can have proteins, you can have microRNAs, and you can have genes, and you have them upregulated in red and downregulated in blue. Okay. Here are the list of the pathways that are more altered by these 20 hubs, the processes and the geo processes. Just to look as an example, for example, here you have from that list, for example, this first one is the role of microRNA in cell proliferation in colon cancer. This has already been proven. So, is this pathway here? As you can see, we have several microRNAs that are altered down or up, down, up, and changing some pathways. Okay, and also for migration, survival, angiogenesis. So then, for example, this microRNA is overexpressed and is targeting all these proteins. Okay. Another remember the Eprin and microRNAs. This is the Eprin receptor. Eprin receptor is changing this pathway that leads to inhibition of cell regulation. Okay, it leads to invasion, metastasis, etc. So If we take all the external and concentrate in the processes, we have here, we can see that neutrophil regulation is one of the processes that is alterated in this cancer. I'm not seeing this. Muscle contraction, iron homeostasis, calcium regulation in cardiac cells, metabolic reprogramming, glycolysis, etc. So here we have the process that are being alterated in this. Only with DAGs, DAMs, and DAPs, we can see what are the processes that are alterated in the context. We also look for those 20 genes, DAGs, and DAMs, that if they have mutations, and they have some are amplified, in red they are amplified, in blue they are deleted in the mutation, and there are some small points here that are point mutations. We look at the expression of these genes, all the genes and microRNAs in the stages 1, 2, 3, and 4 of the gastric cancer. And as you can see, they have difference in the expression of them, the markers. And so we decided to see if we could use them to separate tumor from non-tumor. And for this, we use hot curves analysis, with the expression pattern of all the microRNAs or the genes. And we found that all these could be identified if you are tumor or not tumor. And from those here that could separate tumor from non-tumor, we could identify those 5 microRNAs that has an impact in survival, and those 2 genes that has an impact in survival. So low level and high level, low level, high level of the gene. High level, low level, high level. So they are biomarkers that if you want to go ahead, we will have to validate them in a lot of patients. Okay. Okay, this is the group working with me. This one has already gone, and these ones are the group nowadays in the lab. And Renata is now my boss. Questions? So.
Okay.
Yes, I guess.
Yes, we have the actually we don't need the just to register our online meetings. Thank you so much. Thank you so much for the fantastic talk. Fantastic work. Thank you. I have a number of questions I will ask you the point of view. But there are some authors that work with stochastic mathematical models. And those authors hypothesize that beyond gene mutations, beyond epigenetic alterations, stochasticity can also have some role Yes. Spirogenesis. What's your opinion about this?
Well, I am an experimental researcher, but I think that can be because the cell is always submitted so much interference that the competition between these interference could make stochastic accumulation of small things that at the end could give an effect, really. But it's not my place. I don't know if I can respond very well, but I think yes. I'm going to give you something that I have discussed a lot with Francisco. Much of the diseases, they have two types. Much of these cancers have two types. And normally, the first type is the one that is the more frequent. And more frequent, really, 7% stays always, all the life in that point, and never go to other stages. So that the people think that they are different entities. For example, for breast cancer, the people think that they are luminal, they are hair, or triple negative. And in our thinking, it's not that. They are luminal, something happens, the hair, it starts to proliferate very quickly, and proliferation makes mutations. And the first mutation is the amplification of HER2. And HER2 is that HER2 tumors are tumors with amplification of the locus of HER2. So it's something that happened between one another, and it's normal that replicating cells have these effects, gain of genes or loss of genes, or even mutations. It's normal. So I think that it can be an accumulation of small effects that could really lead to a stochastic effect.
Okay, I know you realize that this one more question, how to water fast, you know. What do you think? Recently, we have seen the appearance, the disponibility, the availability of lots of single cell transcriptome states. My question is, do you consider single cell transcriptome in your analysis? What's the potential of this analysis? What do you think about that?
I think that's very important. Very important, because we don't have just one clone in a cancer, in a tumor, in a sample of tumor. We don't have just one clone. You can have several clones, and you can have some clones that have one activity and others another, and sometimes one clone proliferates and is more frequent, and the others don't. But you have it here, it's there. It's making something, it's making. It's still there. It's not being released. We are starting to use these information of single cells. For example, I have a work where we analyze the exosomes of the tumor cells that are in the plasma. Here, I analyze the plasma completely. But when you analyze the exosomes, they are concentrated in the molecules that the cells are putting outside. And for metastasis or for communication, I don't know. And one thing that we identified very strongly was the complement proteins. And complement is one motive of the innate immune system. So it's there just to make anti-tumor function. But the tumor is there. So the cell has not functioned as it should be. So we thought, well, this complement proteins comes from the tumor or the microenvironment. Because when we select plasma, we select everything. So we use the single cell transcriptomic to identify in our proteome analysis which cells were delivered, what were the frequencies of each contribution of each cell. And at the end, it was the tumor cell that was releasing complement and not the macrophages or the hepatocytes. So I think that's very important to have a lot. But it's still at the beginning of the use. And we don't have enough studies. For example, when we look at our samples, we found that the principally was the basal cell that was secreting the exosomes. But the basal cell used to cooperation was the tongue, basal cell of the tongue, and not of the breast. So I think that we will have more results in a few times.
Thank you so much. I have more questions, but I will stop you. Thank you again. Very good. That's nice. Thank you.
About the gastric cancer is the gastric cancer is a very dangerous disease that the chance of survival of human is really less. That we have very certain in Pakistan that every 5%, 1% is going to find HIV. Is HIV that much dangerous that you must mobility or something like that, or not? As you said that the chance of survival is really low.
It's very low because the cancer is discovered very late. When it is discovered, you have all the stomach with cancer, all the tissue is cancerous. Okay? So you don't have some symptoms early. You only have symptoms when the tumor is very advanced. Okay? So it's to screening for gastric cancer.
This epigenetic part that is about a gene being activated or disactivated, has something to do with the geometry that takes the topology and the chromatin.
DNA, human DNA is not alone. It's not a molecule alone. It's a molecule organized with chromosomes or chromatin. And the compactation of chromatin and chromosomes depends on histones. And histones have a code. Each nucleosome has 8 stones, there in stone, and you have another stone outside, linking the nucleus on the edge of the DNA and the outside of the DNA, it's linked. So the process of replication and transcription depends on the compactation of the chromatin. The chromatin is very compact and cannot have access of transcription factors that are going to activate transcription. So if the acetylate histone H3, you compact chromatin. If you deacetylate, you change the topology of the chromatin, and so you express a gene or not a gene.
So from a physics point of view, it's like an energy condition of a membrane. And it's here because that configuration, that topology is associated to some chemical links.
Yes.
And then there is any way that is to act differently, like to break this link, to change this topology, to because this also, some people some time ago were working with
what we call, it's also complex, everything is complex in itself. There are complexes that are, the function of them is exactly compactation and decompactation. And you have the polycomb complex that are groups of proteins that have several enzymatic activity like the methylase, acetylase, etc. And these proteins, this complex, normally close the chromatin. And you have another complex, for example, the tritarax, that opens the chromatin. They are not one protein, they are a complex of proteins. And if you have mutation in one of the tritarax protein, for example, you have more aggressive leukemia in the world. It's a leukemia that starts in the uterus. The baby born with the leukemia. Because you are opening the chromatin, so you are mutating one gene, but you are doing several genes to be expressed that should not be expressed. And all these genes are developmental genes, are genes that are active during our epigenesis. So they are important exactly for proliferation, differentiation, regulation of proteins, etc. And those genes, if they are alterated, they contain several.
Thank you very much.
I think about data because I see some people prefer to use RNS instead of people now that we start to have single cell. What I guess you is that science is artistic together because this data that has not been completely analyzed. Now we have another practice that single cell. I guess single cell is going to
we must use those. If you start and finish with single cell, I think that the question will be so complex because you will have quantity. In one sample, you have several kinds of single cells of the tumor. Epithelial single cell with different sequences. Okay, so I would use directly single cell. I think that single cell would be important to answer specific questions. Okay, if you have an idea of what's happening, and you will ask, okay, but this is really this or can be this? Okay, so I think that you will deal with frequency because the clones in the tumor, especially for breast cancer, they will be a tree with several branches. Okay, single cell is very important to identify exactly the initial mutation. It's very important for this, because for this it was developed. Because they wanted to identify what was the first mutation. And some tumors have the first mutation. Breast cancer don't have the first mutation. Breast cancer don't have a founder mutation. Okay? Yes, it has a founder, it has a risk mutation for hereditary breast cancer. There is CR1 and CR2. But for sporadic cancer, it don't have. The most frequent mutation in breast cancer is P13 kinase. And it appears in the luminal way supply and in the frequencies of less than 30% of cases. So it's not a founder mutation. A founder mutation has to appear in 100% of the tumors. Okay? So there are tumors with founder mutation. For breast cancer, we don't know how it starts. We don't know. Probably there are a collection of polymorphisms always. And this is being attacked by a project from NCA in the United States that we are participating, that is going to sequence the whole genome sequencing for 300,000 women with breast cancer in 300,000 controls without cancer. They are going to sequence everybody and see what are the polymorphisms that combined could have a greater risk for breast cancer. Okay.
And really big fan of you. And since I'm younger here, like I said, I like to my grandmother. So, just one small question. We talked about a lot of transcriptomics. Besides that, what's the other omics that you bring as a
Oh, I think that proteomics is very important. I think that the integration of at least transcriptomics, proteomics, and regulatory RNAs are very important. Because this makes the expression pattern of the cell. It's not the RNA that is functional. The functional is the protein. The protein are the machines of the cell. So if you have the RNA, you don't have the protein, doesn't matter. Okay. So in what we tried, we started with proteomics, then we went to transcriptomics and more recently to microarrays. we have to add long coding RNAs that are also very important because they act as sponge to microRNAs. So, and you have the microRNA, but if you have the long coding, they will take out. That's it. So, that's it. And now we are entering the microenvironment. We are trying to work with the microenvironment. Yes, where sound will be important.
Excelente. Então, somente para as pessoas que estão na...
Sorry.
Não tem pergunta no chat, não tem. So we are going to stop the morning section, and we are going to resume in 1.5 hours. So whatever is the fuse of different people here connected, is what we are going to resume at 1:30 Rio de Janeiro time. So thank you very much and see you later. We will have a different link for YouTube that will be posted on the conference webpage. Thank you very much and see you in a little bit. Thank you.
Foi aqui, eu acho. Você gerou o link?
Sim, mas vamos tirar outro.
Sim, tá. Sim, porque senão você pode ficar aberto por tempo inteiro.
Sim. E a pessoa que recebe, porque eu agora, você comprou antes. E tinha aqui,
só para ver pela
online.
Está muito bonito. A gente dá um jeito de tentar. Você só precisa botar o microfone direto no computador ou botar esse computador na mesa, que aí ele acha que de repente ele consegue publicar. A imagem vai ficar complicada também.
Caraca, putz, o set é complicado.
Você consegue tirar?
O som, tá, desculpa.
Não, uma vez que você não muito colocar esse daqui, que vai sair na caixa do som. Entendeu?
Pode ser.
Isso que a gente fez a última vez. Coloca o microfone, porque vai ser daqui, o cara que fala lá fora.
Caraca, vou falar com ele lá então.
Deve ter como fazer, né?
Onde é que vai aparecer o link?
Tá ouvindo muito mal.
Onde vai aparecer o link?
Vamos embora.
Vai aparecer o link. Vamos embora. Tá bom? Tem um monte de gente lá esperando.
Tá bom, obrigado. Eu vou mandar para o professor aniversário. Aniversário da professora Eliana, vamos pelo menos botar um parabéns para ela.
Assim, não, tem que ser uma versão ali, ó.
Professora, deixa eu conversar, nós vamos dar um parabéns para você.